Now that we have talked about ions and making ions and electron configuration, we're going to talk about the energy involved in making those ions. There is something called ionization energy and electron affinity that we want to look at. We're going to start with the ionization energy. Let's define it. It's the minimum energy required. It is a required value. It takes energy to do this. To remove an electron, and we have to define which electron. We're going to remove an electron, the easiest one, from a gaseous atom in its ground state. Now that gaseous atom in its ground state is the way that we can define it so that we can make a comparison across the elements on the periodic table. If you remove an electron that's in an excited state, it's easier to pull off. If you put it in a solid, it's a different energy than if it's in a gas state. So we make that just as a common ground statement. We're going to put it in a gas state. We're going to remove an electron from this atom, and what's the minimum energy it could take to do that? Because if you use a lot more energy, it's going to take off the electron too. We just want to just get it off. How much energy is that? And that is ionization energy. We abbreviate it IE for ionization energy. So this is always a positive value. It is the energy required. Remember, endothermic required, positive in sign. So this is always a positive value. It is going to be a measure of how tightly that electron is attracted. So it is attracted. Remember, we've got our nucleus with its positive charges. We have our electrons in these shells being attracted by what we call the effective nuclear charge. It is feeling an attraction. It is an electrostatic attraction holding those electrons on. If you want to pull this electron off, it is going to require energy, just like it takes energy to pull magnets apart. They're attracted, you have to pull them apart. Even if an atom wants to remove that electron, okay, to get a noble gas core, it still requires energy to pull it off. If the atom wants to get rid of that electron to get that noble gas core, it is probably a pretty cheap cell. It is easy to remove that electron, but it still requires energy. So if it's not attached tightly, it requires not a whole lot of energy to pull it off. So here would be a representation of that energy associated with that process. So we have our atom. Let's say it is since I have three positives here, it's lithium. Its electron configuration is 1s2, 2s1. Okay, we're going to take and we're going to remove that electron. So we take lithium, pull off the electron. What do we have is Li+. Its electron configuration would just be 1s2. So now it's pulled off that electron. Well, where is that electron? It's not on there anymore. So we represent it being pulled off. The G that you see there, because it's in the gas state, this is how we define ionization energy. We pull off the electron from it. It turns into a cation. That cation is still in the gas state. So it's the energy associated with this process. We can talk about first ionization energy, which is what I'm representing here. That is removing that first electron. So the energy associated with this process, the delta H of this process, is equal to ionization energy 1. The amount of energy required to remove it is going to be called the ionization energy. We could also talk about the second ionization energy. The second ionization energy is not the energy to remove 2 electrons, it's the energy to remove the second electron. So you start with this guy, for example, Li+, in the gas state, and now we're going to say let's pull off another electron. So now we're going down to 2+, and it's still just the removal of 1 electron. So the energy associated with this reaction would be called the second ionization energy for lithium. So if we think about these two reactions, here removing an electron from a gaseous atom, and here we're removing an electron from something that has a positive charge, which one do you think would require more energy? Well, hopefully you said it would be the one to remove from a cation, because what do you know about opposites? They attract. Once we remove this electron, these electrons are very more tightly held on to its nucleus, and it's going to be harder to remove the next electron from it. All right, so this will progressively get more and more difficult to pull off electrons. Second ionization energy is always, for any atom, okay, so we're comparing the single atom, this is always greater than this one will be, every time. Let's look at the values for some ionization energies, okay? So let's look at this table. Let's blow it up here a little bit bigger. So we're going to compare our first element of hydrogen. It has 1 proton in the nucleus, and it requires this much energy, and it's in units of kilojoules per mole. So we're removing 1 electron from a whole mole of hydrogen atoms, and it requires this much energy. Helium, to remove the first one, is this value. Notice to remove the second one, it goes up. It always requires more energy to remove the second one. Lithium, to remove the first one, it takes more energy. It takes less energy to remove the first one for helium, because now we're moving it out of the second shell. These were 1s1, 1s2. We were removing an electron from the 1s shell. Now we have an electron that we're removing from the next shell out. So there was some shielding there. So it's not as hard to pull it off. But if we tried to pull the second one off, it really jumps up. Okay, a lot higher. Big jump there, because when we try to remove the second one, we're taking it out of the 1s, the inner shell. So let me just say that again. Let's draw that a little bit bigger. 1s2, 2s1, that's not an s, 2s1. To remove the first electron is this one. It takes 520 kilojoules. Once we've removed that one, to take the next one out, we're pulling it out of an inner core. It's always going to jump up to take one, and it jumps up a ton, a whole bunch. Now let's look here. Beryllium, it's 899. It jumps up to 1747. That's a little bit of an increase, but nothing like the increase that we're seeing there. It's big jump. Why would this be? Let's look at beryllium's electron configuration. It's 1s2, 2s2. To remove the first electron, we're going to take one of these away. To remove the second electron, we're going to take the second one away. It takes a little bit more energy to do that. But if we're going to remove the third one, we have to go into this noble gas core of helium and take one away that doesn't have much shielding, and it's going to jump up. So we're going to always see the biggest jump occur when you're starting to take an electron out of the next shell in. Look at boron. Where does the big jump occur? Does it occur, I'll give it numbers, 1, 2, 3, 4, so that you can answer. Where does the big jump occur? Well, it occurs between 3 and 4. It is much harder to pull off the fourth electron. When we do boron's electron configuration, it's 1s2, 2s2, 2p1. The first electron, 801. The second one does require more, 2430. The next one, but these are all in the same shell. They're all in the same n equals 2. It's taking more and more, but it really takes a lot when we try to take one out of the noble gas core. That's the helium inner core. So after examining that, let's have you look at this trend. I have some element. I'm not telling you what it is, but I'm giving you the ionization energies. These are all in values of kilojoules per mole. Okay? So to remove the first electron is this, then this, then this, and you're looking into removing the electrons. I want you to stop and tell me, how many valence electrons does this element have? Well, if you said 5, you'd be correct. Why did I say 5? Because when I tried to remove the 6th, I have a really big jump that's occurring there. So when I remove the 6th, when I'm removing that 6th one, I'm now reaching in and I am taking the electron out of an inner shell. So this is an outer shell, 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 but this is an inner shell, so it has 5 valence electrons. Now let's look at the trend of this first ionization energy as we go across the periodic table or increasing the atomic number. So we're going to be looking at that versus first ionization energy. First thing we'll look at is from lithium to neon. So we've got our periodic table, and I'll draw a little schematic of a periodic table across here. Okay. Where is lithium? Lithium's here, going across to neon here. So we're moving across the periodic table. And what in general is happening to the ionization energy as we go from lithium to neon? Well, as we go from lithium to neon, we see that ionization energy is increasing. It's increasing as we go this way across the periodic table. That's true for the next group, sodium to argon, it's increasing. It's true from potassium to krypton, it's increasing. So as we go across rubidium to xenon, we see a general trend of it increasing as you move from left to right across the periodic table. Okay? Why would this trend be? Well, what did we know about the size? The size trend as we go across the periodic table. Okay, so we'll schematic out a periodic table here real quick. We know that it got smaller atomic radius as we went across, didn't it? It got smaller and smaller. Why? Because the effective nuclear charge increased. Those atoms are being pulled in smaller and smaller and smaller. Well, if they're being pulled in smaller and smaller and smaller because the Z effective is going up, it's getting held on tighter and tighter. It requires more and more energy to pull it off. So as the effective nuclear charge goes up, the atom gets smaller, but as the effective nuclear charge goes up, the ionization energy is going to go up. It's going to take more energy to remove an electron. So that is the trend across the periodic table. As we go from helium to neon, we are looking at the going down. And as we go from helium down, that noble gas thing, we see that the ionization energy is doing what? Well, it's decreasing, and it's for the same reason. As we go down a group, what's happening to the size? It's getting larger and larger and larger. Those valence electrons are further and further away from their nucleus. It gets easier and easier to pluck them off. So ionization energy always goes down when the size gets bigger for the same reason. What's happening to the effective nuclear charge? It is decreasing as you move down. They're further and further away from the nucleus. The ionization energy is going to decrease. So that is our general trend, okay, of why it is increasing across the period. In fact, ionization energy is increasing across the period because the effective nuclear charge is increasing. It's harder to remove an electron. Ionization energy is decreasing as we go down a group because the atom is getting larger. Hold on a second. Getting larger as we go down, and it's easier to pull off the electrons. All right, so that is the definition of ionization energy. That is the trend of ionization energy, and that is the why for ionization energy. We also looked at first, second, and so forth ionization energies, and we can look at numbers and know how many valence electrons an atom has based upon the values of these progressive ionization energies.